Hello, Management Science 291 students. I'm going to go over the R code for the packing cartons data in the Chapter 13 ANOVA notes. So I've started by reading in the data file, which is available in Canvas. It is a CSV file, so I've read it in using the read.csv command, which we've seen many times now, so go ahead and read that in. I always like to take a peek at the data set, so I did head packing. And now I can see the variable names within the data set. The variable names are station and number of cartons as num cartons. If you want to see the full data set, look back in the notes. I don't want to take up my full console here. And I've also just attached the data set with attach packing. And I did that because I don't want to have to keep referring back to the data set name. And this way, R will know whenever I refer to a column that I'm referring to the column from the packing data set. Okay, so the first thing I'm going to do is make a box plot of the data, and I've typed some things in Notepad here. This is a good little trick when you're working with R. If you want to do your typing in Notepad, it just makes it a little easier to save when you're done. And I'm just not a very good typist, so I'd rather have it written out ahead of time. So let's take a look at the box plot command. My quantitative variable is num cartons. And I want to break that out by the factor stations because we're interested in seeing if there's a difference in means among the number of stations. So that's why I have tilde, and this factor says that the variable station is a categorical variable. It'll actually work if I don't do that here, but we're going to have to do it later on. So I want us to just go ahead and get in the habit of let's treat this station variable as a categorical variable. We used numbers to distinguish between the stations, but it is a categorical variable. All right, so let's take a look at that box plot. And here it is. And as you know, we're going to use ANOVA to see if we see, to compare the variance between groups to the variance within groups. So within groups is the amount of variation we see within one box plot for each individual group. How much variation are we seeing within group? And we want to compare that to the amount of variance we're seeing between groups. So how different are these two groups, and then also between these two groups, basically between all of the groups. Okay, and so we're going to use some formal analysis. We can look at it descriptively and see some things right off the bat. It looks like groups 2 and 3 are quite different from each other. Groups 2 and 4 are quite different from each other. But we're going to do some more formal analysis. Okay, so we're going to now do an ANOVA analysis. And so I'm going to create a new data set called fit over here. And it's going to record some of the values from the ANOVA analysis. So notice over here I have AOV for analysis of variance. And again, I have the same scenario in terms of the variables that I'm working with. My quantitative variable is number of cartons, and then my categorical variable is station. All right, now that's going to not return anything, so don't be concerned. We put it in this new data set called fit. So let's go ahead and ask R to give us a summary of that data set. So I'm going to ask for a summary of fit. And now I have what we call an ANOVA table. And so at the top, I have some of my values for between groups. I have my degrees of freedom for between groups. That is the number of groups minus 1. We have 4 stations, and 4 minus 1 is 3. And we have the sum of squares for between groups, the mean squares for between groups. And then on the bottom, we have our residuals for within groups, our sum of squares for within groups, and our mean squares for within groups. And here we have our F value, and we talked about the idea that our F value is this mean squares between divided by mean squares within. let's go ahead and do some analysis now to test our assumptions. So one of the assumptions is whether we have constant variance in our errors. We talked about this in lecture. I'm just going over the R code for it. And this is the Bartlett test. Now notice here that again, this notation is a little different in the R code. Before we were using tildes, but for this Bartlett.test, we're just going to put a comma between the two variables. And so this is a test of homogeneity of variances. And we saw this previously in lecture, but we're just looking at it again. The p-value is not significant, so there's little evidence against the homogeneity of variance. And when we look at the next couple of plots, this will be a little bit more clear, or it'll be easier to talk about. So let's go ahead and do the next graph. Okay, now if you do a graph and you don't see it immediately, you can always pop up here to this Windows and go to the graphics. And here is the graphical display that we're looking at, our residuals versus predicted plot. And if you could put a little line here at 0, just imagine a horizontal line here at 0 like we talked about in class. And we're just studying the amount of variation we see from each of these residuals to that horizontal line. So in other words, we're looking at the spread here. And the spread appears to be about the same in terms of its relationship to that horizontal line for all of the 4 groups. So it seems like the assumption of constant variance is reasonable to make. We don't see evidence against the claim of constant variation. All right, so I'm going to pop back over to the console and we're going to do another graphical display. This time we're going to do a normal plot. So that's QQ norm of the residuals. And again, if you don't see the graphical display, you can find the Windows option and go over to graphics. You can toggle between the console and the graphics window here. All right, and so there we go. And so along the horizontal axis, this represents what the values would look like if it was indeed from a normal distribution. And then across the vertical axis, we have the actual values. And so if those match, we would have a nice linear relationship. In this particular case, what we discussed in lecture is that it's not perfectly linear, but it's close. And so we said there was little to no evidence against the assumption of normality for the errors. So in other words, if I had a plot here that was grossly different from a linear fit, then I would be concerned about making the assumption that the errors are normally distributed. But here, since it's close to normal, I'll say that we don't have much evidence to reject the hypothesis that the errors are normal. All right, so if you haven't already, I would encourage you to go into R and try to reproduce the analysis and the plots that I've done in this video.